Hello friends, this video on isolation of elements part 10 is brought to you by examfear.com. No more fear from exam. Okay. Now we'll talk about the refining of the metals. So once we have got the impure metal now, this is the impure metal we have achieved now, we have to make it more pure. For this we use refining, and there are various ways to refine the metals. One is distillation, liquefaction, electrolysis, zone refining, vapor phase refining, chromatographic methods. These methods we use to refine a impure metal. This is impure, or else a raw metal, and this is pure. Let's start with the distillation process, a very easy process. Distillation is very useful for low boiling point metals like zinc, mercury. So for these kind of metals which has low boiling point, because in this case what we do is, for this scenario, we boil, right? So this is my impure or raw metal. Since they have a low boiling point, we use this. So we boil this. What happens is these vapors are collected here, cool down, and what you get here is pure metal. Very simple method. Distillation, we use distillation of water. Similarly, we can use distillation of metal also, which has low boiling point. Metal with high boiling point, you actually can't use this process. The next is liquefaction. Liquefaction is used, again, liquefaction means liquid, you have to liquidify it. So we use this for metals with low melting point. We are not talking about the boiling point here. We're talking about the metals with low melting point, which can actually easily melt. For example, tin has a low melting point. So we can use this method to refine tin, to get ultra pure tin. This is my raw tin, because by this time we have got tin, and I'm making it refined now. This is a pure tin. Correct. So here what we do is a low melting metal like tin that is made to flow. So this is a ramp here, this is a incline, there's some angle here. So the low melting tin can easily flow, and you supply heat. So that the metal can melt, right? With this is a melted form. So this metal can flow on this sloping surface, but the high melting impurities, here please note, higher melting impurities, higher melting point impurities. That means impurities which has higher melting points. So these impurities won't melt, and they will be solid, right? They will be solid, and they won't flow. They won't flow, and they can easily be separated. Correct? So you are melting the whole raw metal which has impurities also. The impurities won't melt so easily. That will be in the solid state, but the actual pure metal will melt, and with this slope the pure metal will flow, and this impurities will be stuck here. The next process is electrolytic refining. Here my impure metal is used as anode. This is my impure or raw metal, and a strip of pure metal is used here as cathode, right? So in this case it is put in a suitable electrolytic bath. It has a soluble salt of same metal. For example, if I'm talking about the copper, it will have copper sulfate or copper something. If you talk about zinc, talk about the zinc sulfate. Okay, so for example, I'm doing a purification of copper now. So if you see, this is my impure copper. So copper 2+ will flow from left to right. So at anode, the reaction I have is, I have a metal copper, right? This is a copper metal. Copper metal will form copper 2+ and electrons. At anode, the reaction will be something else. I'll get this copper 2+ from this left hand side. It will get some electron from here, and it will form copper. So if you see this, copper, impure copper will form copper 2 plus, and copper 2 plus is flowing here. This copper 2 plus will get this 2 electron from here and form copper. And gradually, if you see, the size of the raw metal will sink and these impurities will settle down, and what you get on the right hand side is pure copper, because only the pure copper has flown from left to right. So the next is zone refining. In this, we take advantage of the fact that the impurities are more soluble in the molten state. Impurities are more soluble in molten state than in solid state. So in this, what we do is a circular mobile heater. This is mobile heater, right? This is a heater. A circular mobile heater is fixed at one end of the rod, and this is the rod. This is an impure rod, I can say. Impure metal rod. And this molten zone, this is a molten zone actually. The one which you see in light color is a molten zone. It melted because of the heater, right? And this heater moves from one end to another. Since the heater moves from one end to another very slowly, it melts that area, right? So the molten zone also moves from one end to another. If you see, this heater moves, and with this heater, the molten zone is also moving, right? Because it is moving actually very slowly. Very slowly, what happens is this heater moves, and this heater actually melts that area, right? And the good part is this: the impurities are soluble in this molten zone. So if you do the same process 10 times, what happens is, in this area, what you get is impurity, correct? Because every time the heater moves from left to right, heater carries some impurity with it, because the impurities are soluble in the molten state. So if there is an impurity here, impurity gets dissolved in this molten state, and with this heater, impurities comes in this direction. So gradually over a period of time, you will see that this area is the one which has more impurities. And we then cut this area. So this, whatever remaining is my pure metal, right? This process is repeated several times. So at this end, what you get is the impurities. And it is very useful to produce very high purity metals. For example, germanium, silicon, right? Germanium, silicon, boron, gallium, indium, all these high purity metals we purify using zone refining. So next is the vapor phase refining. In this, the metal is collected into its volatile or converted into its volatile component, and it is collected somewhere else. For example, there is a metal here. So we somehow make it volatile. If it is volatile, it will cross this path, come somewhere here, and you will get this component. Once it is retrieved here, what we do is we again make it non-volatile. Actually, we do something here to make it non-volatile so that it drops off here. That's what we do. So for this, it's a two important requirement. The first requirement here is the metal which I am trying to purify, you can easily convert into volatile with some reagent, right? Metal should be made volatile with some reagent, and once it is made volatile, you have to again get back the metal, right? So we should be able to recover metal from volatile complex, right? So first is you make the metal volatile by using some reagent, and then you again convert back into normal metal using again some reagent, right? A good example is the Mond process for refining nickel. So in this, what we do is, there's a nickel, react this with carbon monoxide at some 350 Kelvin. What you get is NiCO4. This is volatile. Once you have this volatile NiCO4 here, right, it will all jump here, it will go from here to this path, and all the impurities will be left behind. Okay, because the impurities are not made volatile, only the pure nickel is made volatile. And now once the nickel is here, what we do is we'll heat this nickel, we'll heat this complex actually. So here we get this complex NiCO4. So this complex, again, let's suppose we pass a carbon dioxide here, right, or carbon monoxide. So this complex when I heat with again carbon, and I heat this actually in a stream of carbon monoxide, when you heat this, what you get is nickel and carbon monoxide back. So you have to supply heat here, right, supply heat and some carbon monoxide. So what happens is you get nickel back, and nickel is collected here. So if you see, we could easily convert nickel to a volatile complex, and then we could easily recover metal back from the volatile complex. So this is the prerequisite. Okay, this is called nickel carbonyl actually. Okay, so this is the vapor refining method. Other metals like zirconium or titanium can also be used, can also be refined using this method. So for that we use something called Van Arkel method. I mean, that is also a vapor refining method. Just it has been given Van Arkel method name because in the honor of the discoverer. So this is used for zirconium or titanium. So here what we use, zirconium for example have, I'll react with iodine, I'll get ZrI4, and this is a volatile thing. Now once I have this volatile thing, I'll heat it, I'll get zinc back and iodine back. The concept is all same, the reagents used are different. So next we'll discuss is the chromatographic method. Sometimes for example metals ore has it is used for refining actually. The impure metal has some impurity, and this impurity and the metal, they have same chemical properties. So you can actually you actually can't separate them by the chemical methods. So what we do is we use this chromatographic method. Here we have something called adsorbent. This is my adsorbent. And we have adsorbate. So here the thing which we are trying to use here is, the principle which we are trying to use here is these metals and the impurities, right, they are adsorbed in a different capacity. For example, see this animation, let's suppose, see here, there are 3 different parts in this whole metal, right? But if you see, they are adsorbed in a different level, right? If you see here, so the adsorption capacity is different. The green one is least adsorbed, so it flows slower. The red one is maximum absorbed, so it flows faster. This is the red ball, and the red square one is mediumly absorbed. So if you want, you can just watch my video on this. We have discussed the chromatographic method in detail, how it works. So we have something called adsorbent, and all these metal and impurities are here, right? And the impurities are adsorbed in a different capacity. Sometimes, for example, this is my metal, pure metal. So it is less absorbed, so it is moving faster. The green one is more adsorbed, so it is moving slower. Correct? It is all because of the force of attraction between this adsorbent and the particles. So we also use a term called mobile phase and stationary phase. So this is my stationary phase, absorption. And we have something called mobile phase. This is all my green, reds, and this ball is my mobile phase. So what typically we use Al2O3 as my adsorbent. Here, and the different components, as you see in the animation also, right, different components of the metal is adsorbed at different level. For example, here also, right, this is my, let's suppose, metal, right, impure metal. Now if you see, as it goes down, they are separated. Why? Because the yellow ones are more adsorbed, so it's moving at a slower speed. The red ones are less adsorbed, it's moving at a faster speed. But end of the day, by the time it comes here, they are separated, and can actually separate them.
Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.